Hi everyone. In this video, we're going to be covering spectral signatures. In remote sensing, we use the spectral information of materials or features to be able to distinguish between them and analyze them. Each material or feature reflects energy differently due to their chemical and structural compositions. Energy emitted by the sun is reflected by objects on Earth, which we are then able to measure. In remote sensing, we call this reflectance of energy spectral information. A simple way of analyzing spectral information is through a spectral signatures graph, which is what you see here. A spectral signature shows how much an object or material reflects energy across a spectrum of wavelengths. As we've learned, a photon can be either reflected, absorbed, or transmitted, and what we receive with our eyes and our camera systems is the reflected light. In this graph, we see percent reflectance of photons on the y-axis and the wavelength on the x-axis. For the purposes of this tutorial, we're going to distinguish between three components of the electromagnetic spectrum: visible, which we're able to see with our eyes, and near infrared and shortwave infrared, which are wavelengths we cannot see. The visible part of the spectrum is the easiest for us to interpret because it is the only part of the electromagnetic spectrum we were able to see with our naked eyes. We see the wavelengths in the visible spectrum as colors, while all other wavelengths outside of the visible spectrum are invisible to us. For example, the color blue is actually about 400 nanometers, green about 550 nanometers, and red about 700 nanometers. So now that we understand that colors are actually wavelengths within the visible spectrum that we can see, let's take a look at some common features that we would recognize in remote sensing imagery. Let's start with ocean water, which looks blue to us, but remember that blue is a wavelength. The water looks blue because the wavelength, which is around 400 nanometers, is being reflected the most in the visible spectrum. Water can look somewhat green, but rarely red. That's why these wavelengths are not reflected as much as blue. What about water in the near infrared? Remember that just because we see water as blue doesn't mean that it isn't reflecting, absorbing, or transmitting other wavelengths. Water is particularly simple in the near infrared and shortwave infrared, as almost all these wavelengths are absorbed. That's why we see zero reflectance for most of the near-infrared and shortwave infrared wavelength. Okay, let's do another feature class now. How about soil? In the visible spectrum, soil is often brown, which means that it is reflecting the red wavelengths, which are around 700 nanometers, the most. Blue and green wavelengths are still being reflected, but not as much as red or brown. In the near-infrared part of the spectrum, we see that the reflectance of soil continues to rise and then starts to level off in the shortwave infrared. You can see that soil reflects much more energy in the shortwave infrared wavelengths than it does in the visible or near-infrared parts of the electromagnetic spectrum. Let's try clouds next. Clouds are very white, which means that they reflect all wavelengths in the visible spectrum a lot. Remember that when you combine all colors together that we can see, you get white. In near-infrared and the shortwave infrared, we see that clouds then start to drop off in reflectance. This happens because clouds are mostly made of water, and as we saw earlier with the dark blue signature on our graphs, water absorbs wavelengths in the near-infrared and shortwave infrared, which is why we see the spectral signature of cloud continue to steadily drop. Okay, let's take a look at one more feature class. How about vegetation like a forest? A healthy forest looks green to our eyes, which means that it is reflecting more green wavelengths than blue or red. This is why we see a dramatic bump in the reflectance of vegetation in the green wavelengths, around 550 nanometers. What about vegetation in the near infrared? Probably the most dramatic change in reflectance we've seen so far, forest is shown to be very highly reflective in the near infrared section. This is largely due to the structural and chemical compositions of the leaves, which highly reflect near-infrared wavelengths. In the shortwave infrared, forest is shown to be variable depending on the wavelength. We see that forest reflectance declines and falls with an overall downward trend. Okay, so let's wrap up now. This is the final product of our spectral signatures graph, which shows us how water, soil, cloud, and forest reflect photons at different wavelengths in the visible, near-infrared, and shortwave infrared sections of the electromagnetic spectrum. The chemical and structural compositions of each feature cause reflectances across wavelengths to be different from one another, telling us how much energy a particular feature class reflects for each wavelength. A real-world application of this information would be to determine which wavelengths would be best for differentiating amongst features in a remote sensing image. For example, for water we see relatively high reflectance in the blue wavelength, around 400 nanometers, and very low reflectance from around 900 nanometers onwards. Using this information could help us differentiate water from other features in an image. Soil reflects red, around 700 nanometers, quite a bit, and is also highly reflective in the shortwave infrared range, around 2500 nanometers. Using these two wavelengths could help us differentiate soil from other features in an image. Cloud is unique in that it reflects highly for the whole visible spectrum and has low reflectance at around 2500 nanometers. These wavelengths could be used to help us differentiate clouds in an image. And finally, vegetation reflects green, around 550 nanometers, a lot, and has a big spike in reflectance in the near infrared, around 1050 nanometers. These wavelengths could be used to differentiate forest or vegetation in an image. One can quickly see that understanding the spectral signatures of features can help us to distinguish them within remote sensing information and lead to high-quality analyses.